All right, welcome. Today, we are going to tackle a really powerful technique in Calculus 2, finding the volume of some seriously complex 3D solids. It's a clever method that works by slicing up these tricky shapes and turning them into problems that are actually pretty simple to solve. So let's get right into it.
But first, I have a question for you. What on earth could a simple, everyday loaf of bread possibly have to do with university-level calculus?
Well, the answer might surprise you. Pretty much everything. Believe it or not, that loaf of bread is the perfect mental model. It's the key that's going to unlock this entire concept for us. So let's start right there with that core idea. We're going to connect this thing you see every day to a really fundamental principle in calculus. Just picture it. You've got a loaf of bread sitting on a cutting board. Let's call that cutting board our XY plane. Now, every single slice you cut has a certain area, right? Well, if you could find the area of every single one of those slices and then add them all up, what would you have? You'd have the total volume of the loaf. That's it. That's the entire idea in a nutshell. Okay, so now let's see how we can translate that simple, intuitive idea into the formal language of calculus. We're about to turn our bread analogy into a seriously powerful mathematical tool. You know, the official name for this is the method of volume by slicing, or volume by cross-sections. And those slices of bread we were just talking about, in calculus, we call them cross-sections. We're literally just adding up the areas of an infinite number of super thin slices across some kind of base region. And this is the magic formula that does all the work. Now, don't be intimidated by the symbols. That big curly S thing, that's the integral sign, and it just means sum. It's a fancy way of saying we're adding things up. And what are we adding up? The area of a single slice, which we call A of X, all the way from point A to point B. See, it's just our bread analogy written in math. So you might be asking, well, what's the area of a slice? Great question. It totally depends on its shape. This table right here is your toolkit. The problem will always tell you if your slices are squares or semicircles or triangles. And that S you see in all the formulas, that just stands for the side length of the shape, which is something we're going to figure out using the functions that define our base. We'll see exactly how in just a second. Now, to make this absolutely foolproof, I'm going to give you a 5-step blueprint. Think of it as a game plan that you can use to solve any of these problems every single time. Okay, here's the roadmap. Step 1, you've got to figure out your base region. Draw it on the graph. Step 2, find the length of your slice, S, which is almost always just the top function minus the bottom function. Step 3, pick the right area formula from our toolkit. Step 4, you plug that S you just found into the area formula, and that gives you your A of X to put inside the integral. And finally, step 5, you just solve the integral. That's the whole process. All right, theory is great and all, but let's see this thing in action. We're going to take our 5-step guide and apply it to a classic problem you're definitely going to see. So here's our setup. The base of our solid is a circle, defined by the equation x squared plus y squared equals 9. And stacked on top of this circular base, we have a bunch of square-shaped cross-sections. Our mission is to find the total volume. Let's follow our steps. 1. The base is a circle with a radius of 3, right? So our interval along the x-axis goes from -3 to 3. 2. We need the side length s. That's the distance from the top of the circle to the bottom. So that's the positive square root of 9 minus x squared minus the negative square root, which simplifies to 2 times the square root of 9 minus x squared. 3. The area formula for a square? Easy. That's just side squared. 4. We plug our s into that formula, we square it, and we get our A of x, which is 4 times the quantity 9 minus x squared. And all that setup work leads us right here to this nice, clean integral. This single expression represents the total volume. And honestly, the hardest part is over. Getting to this point is the real win. Now, all we have to do is evaluate it. And after you compute that definite integral, you find that the total volume of this pretty unique solid is exactly 144. Now, here's where this whole method gets really efficient and kind of cool. Since we've already done the hard work of setting up the integral for the side length squared, we can now solve for other shapes with a really clever shortcut. So, let's pretend the cross-sections were equilateral triangles instead of squares. The base is the same, the side length S is exactly the same. The only thing that changes is the constant in the area formula, that square root of 3 over 4. So we just take our previous answer of 144 and multiply it by that constant. That's it. We get 36 times the square root of 3. No need to redo the whole integral.
And guess what? It works for semicircles too. Their area formula has that constant pi over 8. So we just multiply 144 by pi over 8, and bam, we get the new volume, 18 pi. This just goes to show you how powerful this method is once you have that core integral figured out.
But you might be wondering, what if the base isn't a simple shape like a circle? No problem. Let's see how the method works when the base is a weird region trapped between two curves, like y equals x and y equals x squared. The process is exactly the same. Our base is the area between those two curves, which, if you graph them, you'll see they intersect at 0 and 1. The side length s is just the top function y equals x minus the bottom one, y equals x squared. We plug that into the area formula for a square, set up our integral from 0 to 1, and evaluate it. The final volume is 1 over 30. See? The blueprint holds up no matter what the base looks like.
So there you have it, the power to find the volume of almost any solid just by slicing it up into familiar shapes. So my final question for you is this. Now that you have this tool in your back pocket, what kind of real-world objects, from mountains to engine parts to architecture, could you now finally measure?